I think I got everybody's quiz back. If you don't have it, I don't know, I think I have everybody. Okay, so we're kind of gonna do today, I guess, what is helpful for you. So I don't have too much planned, although I can jump into stuff if we want to. But I wanted to start talking about like when the homework is due, when the exam's going to be due, and let's figure, or when the exam is going to be, and let's figure out that. So I guess I can start by saying what I have heard from some people. So I know there is a physics exam on Monday. So I'm a little reticent to push the exam to Monday because of that. So I've heard that. I know that there have been a number of questions about the homework due today. I'm hesitant to change the deadline too drastically because if we keep the exam on Friday, I want you to have solutions so that you have time to study. So I don't want it to be like, oh, we'll push the homework back till Thursday, because then that doesn't really help anybody. I mean, I guess on balance, I don't particularly care when these things are due. I would be okay pushing the exam back to Monday if that, I mean, it overlaps with a physics exam for a lot of people. I would be okay doing that. I don't particularly mind that. It would probably mean that then there is a homework set that would be posted, so we're not like getting too off between when homework is due and when we're covering things in class. We'd probably have like a homework set that I released on Friday, like this Friday, that would be due the next Friday. So there would be, I guess, an overlap there, but I'm happy to do that. So I guess so the moving parts are when the next homework would be due, when this exam overlaps with exams in other classes, things like that. So I'm happy to hear what you guys think, because you're the first class and we need to come out with something decided. You guys get to be the arbiters of the deadlines for you and the other class. But does anybody have any strong opinions or comments?
Can the homework be due at midnight tonight instead of?
So I've heard that from a number of people. Megan?
You know what, we both have our physics exam Monday right before this class. Yeah,
so I heard that from a couple people. So I think that would be my argument against moving it to Monday. So unless anybody has really strong desire to make it Monday, I would rather have it Friday because of that.
Can it be Wednesday, or is that too crazy?
You can always shoot for Wednesday.
So no, I mean we can talk about it. I hadn't thought about Wednesday. What is the general thought on that? I see very large shaking of head in the back from Josie.
I have an exam on Wednesday, so at least
Okay.
Next week is when like a lot of classes have exams anyway, but like also I think whatever day it is, people are gonna be able to do it. That's my thought. Like you'll make it work.
I mean,
So,
there's
as
no.
long as the homework's not due until midnight.
So there's no perfect day for anybody, and Friday is the day that was planned.
Take home over the weekend.
A take home over the weekend. So that's a different kind of exam. I mean, we could do something like that. I'm hesitant to totally change it up.
Sunday morning.
Yeah, we'll meet here Sunday morning.
I'll come in Saturday and we'll have like a 4-hour exam Saturday. Okay. So what I'm hearing is there's not like a perfect time for it. Would it be helpful to make this homework due at midnight tonight?
Yes.
I think it's.
Okay, so we can for sure do that. That doesn't mess up. I mean, we'll talk about some of the stuff today in class, so hopefully that relieves some of the pressure. Like, oh, I want to see the solutions because I need to study with that. I think there's enough other stuff. I mean, how many days in advance do you really start to study? But there's enough other stuff that's going to be on the exam. So hopefully it's not going to be just this last homework set, obviously. So if we made, I guess, if we made the homework due midnight and said, then that gives you a help session to go to. If we're going to talk about it obviously in class right now. I'll release the solutions like Thursday morning at 7 or something like that. And then we'd still keep the exam on Friday. Is that the general agreement that would be okay?
There are people in the 1 o'clock section, like 5 people that asked me to get it moved to Monday. But I don't have a strong opinion about it.
You are, right, you guys are the ones in charge, so.
Exactly.
I mean, I
So
see,
how well should I execute
Joey, so I heard like mutterings of moving it to Monday, but.
We've been through a lot this year. I think we deserve a take home.
I don't know, I mean, take home's not that.
Zoom Sunday church now. As long as you perform a service on Sunday morning and we're here, we'll take the
For
exam.
a service.
I don't even know what that means. All right, we're veering from the helpful to the not as helpful. Okay, so I think that sounds like at least there's broad consensus that that's not terrible. So we'll move the homework to midnight. And we'll plan on keeping the exam as is. If there's something for you specifically that doesn't work well, let me know and we can take it virtually some other time or something like that. But let's do the exam Friday as it was on the schedule. Keep the homework due, move the homework to due midnight. That sound good? Okay. Yeah, so if there's some specific circumstance that you have, let me know and we can figure it out. Okay, so you just got the quiz back. And let me get this rolling. All right. If that works. Okay, so you can see, people online can see, I think we're all set. So for the quiz specifically, let me just pull up. Just to kind of go over that briefly. So kind of how to think about this, remember you're choosing for part A, which is at higher pressure. I think this is really like to kind of help you think through this problem. It feels a little weird because the thing is upside down, but you can think about it really the same way. Like which is pushing harder, just visually? Well, it's the one that's winning. Like it's pushing its side higher than the other side. So it's the one that's the higher pressure is going to be 2 because it's kind of winning the battle. It must be pushing harder. The difference in pressure, so you're going to find a spot at the same elevation. So we'll call that A and A prime. So here, PA equals PA prime. You can't do that same thing down like here. You have B prime and B. So PB is not equal PB prime. And those don't equal each other because there's a different fluid in the middle. So it has to be the same elevation, but it has to be a continuous stretch of fluid. So that's maybe a thing to know. So we need continuous fluid and same height or same elevation. And then really what you're going to do is say, okay, so if we look at the pressure at PA and the pressure at PA prime, you can write out an equation for all of those for exactly what that's going to be, and then you set those two equations equal to each other and then solve for the unknown. So what you're going to have for PA prime, that equals P1. Then we're going up, we'll call this distance like H2. We're going to go up a little bit from that. So we go minus, this would be rho water G H2 minus rho oil G H. So again, we're starting at A prime and we're going, so it's going to be equal to those, and because we're going up in the fluid, it's going to be minus. We do the same thing. PA would be P2 minus rho water G H2 minus rho water G H. Then we would set those things equal to each other, cancel stuff out, and what we would get is P2 minus P1, or delta P, equals the difference in densities, so rho water minus rho oil times G H, because those two would cancel each other out. So you would just get those difference in densities. And maybe that works again, if you think of like the analogy of the scale, the P2 on the right is holding up the exact same thing so the thing on the left is holding up the exact same thing, but it's holding up 9.4 millimeters of oil on the scale. And P2 on the right has 9.4 millimeters of water on the scale. And water is a little heavier than oil. So the extra pressure is how much heavier that water is than the oil. So the answer was, it takes a little bit to get the units, but this was like 16, maybe 16.6 or something pascals, which is, right, a pascal, so that's 16.6 newtons per meter squared. Okay, so you first need to find the spots where you know the pressure is equal, and then kind of say, on each of those scales, what's the actual weight sitting on those scales. Set those two equal together, and then actually go through and solve for your unknown. It's usually, especially when the geometry gets weird, don't skip steps and just like jump to what the answer is going to be. It helps for you to think through it logically, to just go through step by step. Any questions on quiz? Okay. Are there questions on the homework? I know that there are. So what questions are there on the homework? Yeah, Liz.
For just in general for 3 and 4, I need some help with like the finding the resultant force. It's like the integral thing.
Okay, so a resultant force, the equation that we have for resultant force we have two parts. One is the magnitude. Three parts, I guess. Magnitude, direction, and location. Right, so if you want to figure out what the resultant force is, you need these three things. So each of them there's going to be a separate strategy to get it. The magnitude right, that is the sum of the pressure times the area. Right, that would be the magnitude. It's the pressure summed up over the area. So what does that look like? That would be something like this. And this is the integral you're talking about, right, Liz? Okay. So this would be the equation that we typically get. So what does that equation actually mean? It means that we're adding up the pressure times area over the whole surface. We never actually really do that integral because we don't need to. So if you add up the pressure, like pressure times area over every little snippet of the whole surface, another way of saying that equals, this equals the pressure at the centroid times the area. So this pressure is the average pressure over our shape. Right, so the pressure, again, I'll draw like a simple picture. If we had something like, this wall, okay, and we wanted to say, what is the average pressure over this wall? Well, at the top of the wall, the pressure is going to be atmospheric pressure or zero gauge pressure. At the bottom of the wall, it's going to be, well, let me draw a vertical wall because that's going to be easier to look at. So let's do it over this vertical wall. The same idea. Okay, at the top of the wall, it's going to be zero gauge pressure. At the bottom of the wall, pressure is going to be, right, if this is H, P equals rho G H. And it's going to be increasing linearly between those 2 points as we go down. So the pressure is going to be pushing on the wall like this. Right, where there's very little force on the top of the wall, there's a lot of force on the bottom of the wall. If we wanted to, like, we could break this up into little snippets and basically add that up over the whole surface. And there's going to be, a little bit at the top, but the other way to do that is to say, okay, so this is a triangle. So what is the area of that triangle? It's 1/2 base times height. Or it's, right, so 1/2 base times height, or it's the same as the area of this square, right, which is the pressure at the centroid. This is PC. Right, so the overall magnitude of those two pressure distributions would be identical. Does that sort of clarify? So basically, you're never gonna, like, simple way, you're never gonna, so don't use this. Use that. We're never going to actually need to do the integral because it's just the average pressure, which we can find as long as we know the pressure at the middle of the object. So that's how we're going to find the magnitude, right? That's magnitude. The second part that we need to find is the direction. The direction is always, it's always normal pushing in on the area, on whatever object it is. So it's always pushing in, whatever the shape is. You can just look at the shape and it's right, it's pushing in on that. And then the location of FR. So this, again, there's like a couple checks that you can do. The number one check that you can do, it's never going to be in the middle. It's never going to be toward the top. So it's always below the middle, but it's not going to be like at the bottom either. So it's always going to be somewhere between the middle and the bottom of the shape. So this is always, so below the centroid, but not to the bottom. So depending on the geometry, maybe it's like kind of close to halfway, maybe it's more close to the center, but it's always going to be between the center and the bottom, a little bit below the center, again, depending on geometry. But that's when you're doing your calculation, that should help you like at least place if you're in the right ballpark or not. And then the equation, our book has a couple simplifications of this equation. I prefer to use this one, so it's rho g sine theta over FR. So you can do some simplification because like the resultant force is going to have rho and g, and it's going to have some of those things in them. So you can like simplify and cancel out on the top and bottom of that fraction. But you're going to have calculated, like plugged in your calculator, an equation to figure out the magnitude of the resultant force anyway. So that's going to be like the line above on the calculator. So it's not like extra work to use this one. So some of the simplifications don't work in every circumstance. So that's why I caution against using some of the other similar type equations that our book has. Yeah, Hans. How far below the geometric center? Yep. So you have to be a little careful because like where you define your axes, like where's the origin is going to matter, but you're right, Hans. Like it's going to be, this is I lost my pencil. This guy is the geometric center for the centroid, and this is how far below the centroid. So again, you have to like, especially when you start tilting your axes, you have to keep track of exactly, what are the angles and where this is on the shape. But yeah, I think I agree. That's a helpful way to think about it. Okay, are there any specific questions on either 3 or 4, or I guess one of the other ones? Yeah, John?
For number 3, I was having trouble finding where the length of the channel comes into play.
Okay, so for number 3, you have a situation like this. So this is like the top-down view. You would have something like, there's one gate, there's your other gate. This is 34 meters. I'm kind of making this up. Let me pull up my pictures so that I'm not totally making it up. Yeah, that's right. So that's 34 meters, and the book gives you those axes, or I guess, do they point X that way? So that's Y, and that's X in their picture. They say that angle is theta 15 degrees. So because your gate is angled in the channel, right, this distance here, the width of the gate is going to be longer than 17 meters because it's tilted a little bit. So you end up having to use some geometry to figure out how long the gate is. So it's going to be like between 17 and 18 meters. It's going to be a little bit longer. And then right, you're going to be, the channel is 10 meters deep. So you're going to find the magnitude of the resultant force by, right, the magnitude of bar. So this is going to be like 5 meters underwater. Right, that's where the center of the object is going to be. And this is the surface area of the gate. So that's like, is it 17.6 meters times 10 meters? I think that's right. So you're going to find the magnitude. It's going to be acting below 5 meters by a little bit. So like you should expect something between like maybe 5.5 and 7, something like that. Below the center, but not at the bottom. And then the last part is the like the direction. So when I solved this, I made like a new set of axes that were in line with the gate. So I made axes like this because that made my life easier. And then you figure out a resultant force that looks, right, your resultant force is going to be pushing in on the gate. I can make that in red. Your resultant force is going to be pushing in on the gate, FR. It's going to be centered like left and right, but below centered, it's going to be deeper than the center. But it's going to be centered left and right. But it's going to be pushing at that angle. So then like the last step in this problem is to then do some geometry. And basically what you're trying to do is find, right, split this up and say what component is pushing that way and what's the component that's of the force that's pushing that way. So you would get like, what's the actual force that's pushing the gate, like pushing against the gate versus like the force that's pushing the gate into the other gate. So that's the significance of like their axes. But some of it is just to figure out, like what we're trying to do in this is to figure out the magnitude and location so that then we could do like a statics type analysis on the system and figure out where the moments are and do some of that stuff. We're not doing all that part. We're just finding like, where's the force? How big is it? Where is it acting? What direction? So you're going to end up with something like you have to do the geometry to split your resultant force into those components. If you have like a follow-up question, I'm happy to answer it too. Yeah, John?
So just to be clear, did we not need the length of the channel, or?
You needed the length of the channel to find the size of the gate. After that, it's gone. Oh, the length of, so. Oh, no, that doesn't matter. Right, because it's the same force whether you're holding back like a channel that's 1 meter wide or if it's the whole ocean, right? So pressure only matters with depth. So it doesn't matter how much water there is sitting on the other side. It's just about depth. Yeah, Josie.
Is that? I was a little confused as to whether it's like similar inertia just for like the area, because when I was looking for like the equation for it, it also the mass for some variance, so almost like the area.
It's just so for this, it would be 1/12 width length squared cubed. Can't read my own writing. Cubed. So then you have to look at, okay, what's the depth, like which is the width? Is it 10 meters or is it 17.6? So this would be, so the width would be 17.6 meters. The length would be 10 meters. There is a chart that I have on Moodle that, let me pull it up so that you can see it. That has all equations for normal shapes. It's just the area, yeah, it's the geometry, it doesn't matter what the mass is. So it's going to be this, this document on Moodle. It's exam 1 handout, has the geometric properties of areas. So it gives you things like this. So we would be, oh, we have a rectangular gate. We're going to use something like that. And this tells you, okay, how would you find the centroid? Like if it's a triangle, this is where the centroid would be. This is what the moment would be. So this has just like kind of a handy reference for these types of problems. You'll be given this for the exam. Yeah, Theo.
About the moment of inertia, would that be ISDZ?
So the one weirdness about this, so this, what it calls IX, right? That's the moment of the second moment about the x-axis, which is what we have called IX hat, X hat. So there's a little bit of a disconnect in the terminology from this sheet to our terminology.
But the note. Because you're in the X, Y, and rotating up the Z.
You would be rotating, so the rotation would be like as if this is, I don't know what, it depends on how you're going to be rotating about this axis. Right, because you're pushing below the center, so that's going to cause it to rotate about that axis. But it's yeah, it can get a little bit. Pardon?
I couldn't help it.
So the hinge, you're going to be rotating about the hinge due to the, you're right, you're going to be rotating about the hinge because of the resultant force. But the pressure distribution is going to cause a moment that's going to be pushing harder at the bottom than it is at the top. So it's going to be pushing at that bottom of the gate. So that's where you're rotating around that center horizontal axis, not the vertical axis. So there is another moment about the vertical axis, which I think the problem as written asks you to find, like about the hinge. But that is more statics than I know, so I told you not to do that because I can't do it either. Yeah, Abby.
For PC, I think I'm slightly confused. Is that the pressure or the location of where the pressure is?
That is the pressure at the center. pressure at the center. So it would be the pressure 5 meters underwater. So if you look at, right, here's your gate. It's, right, this is 17.6 meters. There's water here. This distance here is 10 meters. You're looking for the pressure P C equals rho G HC, where that's, right, you're looking for the depth that that center is. So this is going to be 1,000 kilograms per meter cubed, 9.81, and then 5 meters. That would be the pressure in gauge pressure. Because right here at the, so it depends on how you define your axis, right? So our pressure here at the surface, P, the pressure there at the surface is 0 gauge pressure. You could imagine, for some problems, especially for the second one, you could imagine defining your 0 point underwater. So the pressure at like the origin of your axes could be potentially underwater, or it could be something where like this is a pressurized vessel or something like that, where the pressure at the surface of the water is not 0. So you might have to take that into account. But it's whatever the pressure is at the center. Any other questions on any of these? Yeah,
I
Hans?
want to ask, like, where does the pressure occur? Do you want the centroid and the Y value deep, or just the Y value?
Usually just the Y value is enough, unless it's a goofy looking shape. Like, because this one, it's going to be in the middle in X. So I guess if it were like a triangle, then it's not going to be in the middle of the triangle in X because the thing's funny shape. But I would say generally for what I'm going to ask on an exam and what this homework has asked, right? Because pressure doesn't change in the, like there's no change in pressure in the X direction or in the left to right direction. It's just going to be in the middle. So then it's kind of silly to, yeah. I mean, it's not, if you're looking at, okay, what are the forces on, like this problem actually does. So you have hinges here and you're looking at like, what are the forces on that side? Then it matters where, like whether exactly where you're acting and how far out you are from that. Okay. All right. So I think hopefully this helps as you wrap up, or at least confirm that you knew what you were doing, or that you don't quite know what you're doing yet and need to work on that. But either way is still good. Think for what, so we have 10 minutes. So we won't go over too much because we have the exam coming here shortly. Let me just pull up. Okay. So last time in class on Monday, we looked at and kind of derived this equation equals d dt plus okay, so I just want to spend a few minutes here saying, okay, how does this actually relate to the problem that we did, that you guys worked on the in-class assignment where we had stuff flowing into into this kind of like funky elbow thing, and we had velocities coming out. So if we had, right, I'll just kind of draw it here so that we can remember. It was something like this, and we knew, then we had another thing where we had a hole there. And I think we called this 1, this 2, 3, and 4. Something kind of like that. So if we have flow in, and I think it actually turned out we had a flow in there, flow out there, and flow out there. So if this is V1, V4, V3, V2. What we're trying to do with that this top equation here, Reynolds transport theorem, what we're trying to do is like be as detailed and inclusive as we can with every possible situation. But the challenge then is obviously to get from that to the simplified version that we can actually use to solve problems. And sometimes that's not always straightforward. So for this top equation, I'll just rewrite it down here so that we can rho dv. Okay. If steady state if it's steady state, then there's no accumulation of mass inside of our system. So this part goes to 0. That's the accumulation of mass, right? Whether inside this joint is there, is mass changing with time inside of our control volume. So we get the simplified equation, 0 equals the integral over our control surfaces of rho v dot dA. And then we have to look at our problem and say, where are the control surfaces? Where are the surfaces that we need to care about? So then we need to look at surfaces where we have a flow in or out. Okay, so in this case here, we really have 4 of them, right? We have, this would be, that would be one surface, the A1, this would be a second surface, would be a third and a fourth. Okay, so those are really our 4 separate control surfaces that we actually need to look at. So we can break up this sum to its individual parts. We'll call this over area 1 of rho V1 d A1 plus the integral over A2 B2 d A2 plus the integral over A4 of rho dA4. Okay, so we can look at all of these as, instead of looking kind of all one together, we can look at each of them as a separate thing. And then we have to actually evaluate the value of those specific integrals. Yikes. So what these are, this is right. This would be, say, A1, that control surface. But we need to look at the surface as a vector, right? So this would be, right, the vector notation version of that. So this would be A1 vector, right? It's always an outward pointing normal, right? Outward. An outward normal. What we're going to do then is say, okay, what is the velocity? So if we look at the velocity is coming into that surface, V1. So the velocity here is there. So if we wanted to do the integral over A1 of rho V1 dot dA1, we can first take the density out as long as the density is not changing anywhere. So this is density A1 dA1. And then you have to ask yourself, is this integral is the average velocity times the area? But it's like the dot product of those two. For average, so right, the average velocity vector dotted with the area vector. Okay, so again, if you're summing up the velocity over the entire area, that's just kind of like we did with pressure. It's just the average velocity over that area. So the dot product is where we would actually come into like getting negatives and positives. So the dot product is what gives us our sign. So if this is V1 and A1 are pointing in different directions, that's going to give us a negative in front of that. If V and A are pointing in parallel directions, that's going to give us a positive. So the dot product is going to let us basically flip the signs for us how they should go so that we don't make sign errors. It's also going to allow us to do things with non-uniform velocity profiles. If we don't know, if we have a different shaped velocity profile, we can handle that by actually running through the integral. So we'll pick that up after the exam though. But hopefully you see at least a little bit where kind of the basic equations we came to, where those come from. So plan on an email or on an exam on Friday. Plan on an email, just reminder of what's going on probably this afternoon. But the homework is due at midnight.
Question on